As we discussed in the last video, in the limit of zero Reynolds number, where inertia and the inertia of fluid elements is completely negligible compared to viscous effects, we have what we call kinematic reversibility. In other words, fluid elements don't have really any term that gives them acceleration. If you think about what happens when you are driving a car and going around the corner, or a car that all of a sudden stops, what really gives you the tendency to move relative to the car is the inertia. You have had a certain inertia, and as the car stops all of a sudden, the car changes its inertia, but according to Newton's law, you still like to keep your inertia, and your trajectory deviates from the trajectory of the car. That's why seatbelts are a good idea to keep you attached to the car. Fluid elements, when they flow at reasonably high velocities, have the same kind of phenomena happening to them. The inertia there gives them some idea about what was happening before. If you take the inertia completely out, you have kinematic reversibility, which means that the moment you stop a flow, fluid elements instantaneously, without any hesitation, almost instantaneously, over a very, very short time scale, completely stop, and they don't have any tendency to continue their motion. This will have a very nice effect that is shown in this demo that I will play in a moment. What you have here is a very viscous oil that is sandwiched between two cylinders. So in this annulus, what you have, viscous oil right at the if I bring my mouse on it, you can probably see it in a moment. Right between the two cylinders is where we have the viscous oil. The inner cylinder with a handle, we can actually spin it, we can rotate it as many turns as we like. The outer cylinder or outer wall is kept stationary. So you can see in a moment what I will do with the inner cylinder. The first thing that you will notice is we add some food coloring for visualization sake. So here we put first a red blob of viscous oil right at the center. You can get an idea about the viscosity of this oil just by looking at how it's dripping from the syringe nozzle. Then we put a blob of green color, and or actually blue color. We put the blob of the blue color, and finally we add a third blob of green color. So these blobs of color are just for visualization's sake. They are nothing other than food coloring mixed with the viscous oil. And as you can see, since the density is matched, they stay suspended somewhere in the annulus between the inner and outer cylinder. And now we rotate the inner cylinder. As we rotate the inner cylinder, you clearly see that these blobs get stretched, they get mixed, and you get an idea that what should happen is a pure mixing between these colors. The image becomes more and more mixed mixture of these colors, and there is no clear line that can define the boundary between the three different colors. We did 3 rotations. Now let's see what will happen when we rotate this back 3 times. This is turn 1 going back. We can go another turn. This is turn 2 going back. And then let's do a final turn and bring the inner cylinder to its initial original position. Now this is the 3rd rotation going back. And what you observe is the 3 blobs of dye come back completely intact to their original position. This is what we call kinematic reversibility. In other words, if at any point in a Stokes flow which is dominated by viscous stresses, I stop the flow, the fluid elements don't have any inertia to continue their path. They instantly stop. And if I reverse the direction of the flow by reversing the valves, I exactly walk back through the mathematical solution or walk back through Navier-Stokes equation solution in the limit of Stokes flow to my initial position. There is no way, you can easily see that mathematically, that if you just replace the velocity of the wall to a negative sign, exactly the same solution with a negative sign will satisfy the Stokes problem, and you come back exactly to the same initial configuration. This is a very significant consequence of extremely low Reynolds number flows. And that's the reason, for example, swimming strategies for small bacteria or small organisms are very different from swimming strategies that we have at larger scales. If you take a swimming flagella, for example, in a small organism, you cannot really generate a net lift by usual swimming strategies that we have like humans. Because when you reverse the flow, whatever happens in one direction is going to repeat itself exactly in a symmetric manner in the other direction, and you get a net resulting force that will remain zero. That's why to really generate lift or propulsion in a small or zero Reynolds numbers, organisms have to find other mechanisms that breaks this symmetry and evades the consequence of this kinematic reversibility. Again, as a summary here, you can see an image. What happens here is shown. We started with 3 intact blobs, which were separated from each other. We did 3 runs of rotation for the inner cylinder. Colors got mixed all together. But when we stopped the flow and turned the cylinder back 3 times, we were able to actually get the initial 3 blobs of color almost intact. That a small increase in the volume of the blobs happens due to thermodynamic diffusion, and that's an important concept to keep in mind, because Stokes flow problems, it's true that they have kinematic reversibility, but in terms of thermodynamics and entropy, they are not reversible. Diffusion happens, and that expansion of the color is the small amount of diffusion that has happened. So I hope you enjoy this demo and watch it again, and think about this demo and also parallel to something like a Stokes equation and the mathematical form that we have shown in this review. Thank you, and in the next video we will continue our review.